So part B, even though there already was a part B, the second part B is the same scenario, but now we get a little more specific information. So rather than just this big combined full carton of the empty carton and the eggs, we now have broken apart that we know the empty cardboard container has this mean and this standard deviation. And we get to assume independence, which is good because we're about to combine some random variables. So I'm just going to know, I'm talking about means first of all. So I'm going to be thinking about my full carton that I was just working with in the previous problem. That is a combination of the empty container and 12 eggs. So this is just me saying, what do I mean by full carton? I mean the empty container with the eggs in it. So I can say that the mean of my full container, because I'm allowed to add averages, is just the sum of the empty container, and because I'm allowed to multiply 12 times the average of just the eggs. So technically I should have shown two steps. I should have shown a step where I add this mean plus this mean, and then where I take the constant and multiply by the mean of the eggs. Mean of one egg, I guess I should say, not plural. But I just kind of did it all in one step. But now I'm told some information. Earlier we were working with 840 grams for the average if it's full. This problem just told me the average of it being empty is 20, and we are asked for, if X is one single egg, I'm asked to find the average of one single egg. So this is just 12 times the average of one single egg. And this is just an algebra problem now. So I'm going to subtract 20 and get 820. I'm going to divide 820 by 12, and I get about 68.3 for my average of one single egg. So that's what I'm going to take note of here. Mu sub X is 68.3 grams. Excuse me. So I can do some similar reasoning for my standard deviation. So let me clear some space up a little. So for the standard deviation, I'm still thinking about the fact that I have a full carton, which is the same thing as saying, that's supposed to say empty, an empty carton plus my 12 eggs. Now I have to break apart this and use my rules. You cannot add these standard deviations. You can add the variances and then just square root what you get. So I'm going to think the variance of an empty container plus the variance of one of the eggs plus the variance of a second egg plus, I have to do that until I get to all 12 eggs. Oops, that should not be what I wrote. So the variance of my 12th egg. So if I can sum all those individual variances up, then I can square root it. But unfortunately, I'm going to have to solve an equation because I already knew the standard deviation of a full carton of eggs. That was the 7.9 from the other video. And I'm going to have to write it up here because I'm out of space. So the full carton was 7.9. They told me here that an empty carton is 1.7 for its standard deviation, so I'll square it to find the variance. And then whatever the variance of an egg is, I have 12 of them. So this is 12 times sigma squared x, whatever that variance is, because it's this thing plus itself, plus itself, plus itself, plus it 12 times. So I'd have 12 of those things. So then I'm going to solve this. I'm going to turn this side actually into a variance so I can solve for sigma sub x. So I'm going to square both sides of my equal sign. I'm going to subtract 1.7 squared. I'm going to divide by 12. So I'm subtracting that, dividing that difference by 12. And then I'll square root that to have my standard deviation. So my variance is 4.96. Therefore, my standard deviation of a single egg is 2.23 grams. So again, the reason why this is a 12, and it'd be tempting to want to think 12 squared because I'm multiplying by a variance, but you're putting in 12 eggs, you're not doing one egg 12 times the regular size. So this is not a linear transformation. We are combining these variables of the variable of one egg plus the variable of another egg 12 times. So that is definitely a difficult question.